Hi guys, today we're going to start talking about actual groups of organisms. We've been talking very broadly so far. Today we're going to actually talk about individual things with names. So this is where you have to start remembering names. For the readings, you only have to read the section on, in your textbook, chapter 15, the section on Rhodophyta. We're not going to get to Chlorophyta today, but we will get to Chlorophyta next class. So you can read that too. We'll get through all of chapter 15, but not right now. So just worry about rhodophytes for now. Okay, so who are we talking about today? We are well, this is the tree of life, eukaryotic tree of life, circa 2000. And this is the one that your textbook uses. And it's pretty good. It's pretty good. The overarching idea is that there's about 8 supergroups that share evolutionary history and share some traits. Today we're going to talk about the Achaeoplastids that are in this group, and you can see I've highlighted the 2 groups that are in your text, but there's also some other groups that we're not going to be talking about. But I wanted you to see how this has changed, because this is about 2000. In the last 20 years, there's been a ton of sequencing, and now the eukaryotic tree of life, so the ETOL, eukaryotic tree of life, is based 100% on DNA, and it really has very little to do with traits, even though obviously shared evolutionary history results in some shared traits. And the reason I wanted to show you this is because it's pretty good. I mean, it's pretty robust. Some of the groups get merged. There are some new groups. I don't want you to worry about this. I just wanted to show you that it's changed a little bit, but I want you to stick with the tree of life that's in your text. And for our talk today, it doesn't matter because Achaeoplasta is robust. It maintained its supergroup status in the new phylogeny. Okay, so here are your objectives for today's class. I want you to know what groups are we studying in the Achaeoplasta. Specifically, we're going to talk in a lot of detail about the rhodophytes. What traits do they share? What is their very strange life cycle like? It is bizarre. Where do they live? And why do humans care so much about red algae? So from now on, pay attention to taxonomy, and hopefully you'll know from this class what level is relevant to you. Okay, so this is the same picture I've been showing you for about a month now, right? Shows how eukaryotes evolved via endosymbiotic events. We're talking the Achaeoplasta old placid original event. Now, there was another one, right? They don't show this one. There was this original evolutionary event with this heterotrophic eukaryote who engulfed the cyanobacterium, but there was also a different heterotrophic organism that engulfed a prochlorococcus. And evolution gave rise to Polynella. Now, these are all primary endosymbiotic events, but they're not all archaeoplastids. So that's what's confusing to talk about early eukaryotes and shared traits, because as much as it's satisfying to talk about the evolution of these groups in terms of how many symbiotic events there are, it doesn't always tell the evolutionary story, right? Because as you know, endosymbiotic events can happen multiple times with multiple organisms and lead to very different phylogenies. So today we're going to just talk about the archaeoplastids, which include, for the purpose of our talk, red algae, rhodophytes, glaucophytes, and chlorophytes. They also include bryophytes, but we're not talking about them just yet. We'll talk about them later. So what do you need to know about them? Well, Glaucophyta is not in your text, and I'm not going to emphasize these guys very much, but what I do want you to know about them is they're all unicellular, flagellate. They're in bogs and swamps. They're freshwater, right? There's not very many of them, and that's probably because they're a really ancient group. Scientists think that these algae are very similar to the very earliest archaeoplastids, the very earliest ones that evolved hundreds of millions of years ago. And that's because their plastids are very, very similar to cyanobacteria. They haven't changed very much. They basically look like a bacterium. The thylakoids are concentric. They're not in stacks of grana like they are in other chloroplasts. The peptidoglycan wall is described by lysozymes. and a lot of other bacterial features. I don't want you to worry about it. All I want you to know is that the glaucophytes have very archaic plastids. They're cyanelles, and cyanelles are the type of photosynthetic hardware that bacteria have. That's what's important about glaucophytes for this class. Like I said, your text doesn't cover them, so there's not much else to say. But I have a lot more to say about rhodophytes. And you guys have probably seen rhodophytes all over the place. They're very, very common. They are marine. Most of them are marine, and most of them are macro. And so you'll see, every time you go to the coast, you'll see these. You'll probably see them if you don't go to the coast. I'll show you in a second. But they're beautiful, and they're red, and they look like algae, and you see them all over the place. There's about 6,000 species of them, and they're mostly multicellular, but there are a few unicellular examples. They're the most abundant algae in marine ecosystems, and there are some extremophiles. So some of these algae live in very, very extreme environments, either chemically extreme, like high or low pH, or extreme deep. I'll show you that in a minute, or extreme cold, because there is a if you've ever been on top of a glacier and you see this pink haze on top of it, that's a red alga. It's a unicellular red alga. And I think this counts as an extremophile, an alga that lives on snow. But why are they red? Well, they're red because, not because they don't have chlorophyll A, but because they have phycobilins, and phycobilins mask the chlorophyll A. And that's why when they decompose or they dry out, you can see they are green. And the phycobilins are an adaptation to growing in deep water. Here's some coralline red alga. I'm going to talk about those in a minute, but they look very strange. Okay, so remember from when talking about photosynthetic bacteria, different chloroplasts filtered are active at different wavelengths, which have different properties, right? So the deeper you go, the more the light is attenuated. And basically red light doesn't penetrate very deep at all, nor does purple or yellow. Blue and green penetrate the most. They go to about 200-300 meters. And so they need, these organisms that live down there need a light absorbing pigment that's going to absorb blue and green light. And that is phycobiliprotein. And there's different kinds. The one that is red and gives these algae their red color is a phycothirin. And this is a compound that's only found in bacteria and red algae, but it's really good at absorbing blue and green light, which is a dominant light in deep water. Okay, so the other main thing I want you to take away from the class today is I want you to understand the life cycles of red algae. And that's not an easy task because it's complicated. And it seems strange to me that such simple ancient organisms have such, in some ways, ridiculously complicated life cycles. But superficially, it's not complicated. It is sporic meiosis, meaning there are two multicellular phases. That the haploid and the diploid are both multicellular. And these generations can be identical and be isomorphic, or they can be anisomorphic. One can be big and one can be little. So it's the same sporic meiosis that we've talked about before. So let's just go through it thinking it's just regular plain old sporic meiosis. Let's start with the gametophyte, right? It's a multicellular gametophyte. And here we've got a male and a female. And this is a mistake in your textbook because a gametophyte is supposed to be N, not 2N. So I just noticed this. This is a mistake. I will send out an announcement. Gametophytes are multicellular, but they are haploid, and that's the definition of a gametophyte. And so the male gametophytes produce spermatia, male sex cells in the spermatangia, whereas the females produce egg cells in their female reproductive organs. In this case, they've got a special name. They're called carbogonia. And there's these little, they're very simple structures, but they've got a special name. Botanists love to do that. There's just these little protuberances on the gametophyte, and they have egg cells in them. Now, the only real specialization for the carbogonia are each egg cell develops a trichogyne. And a trichogyne is just an elongation of the egg cell, which allows the spermatia, it fuses with the spermatia is penetrated and confused with the egg nucleus. So far, just a couple of new terms, but it's nothing special. The sperm cells fuse with the egg cells, right? Nothing too crazy. But, and then you've got your diploid zygote, right? And normally this diploid zygote divides mitotically and becomes sporophyte, which undergoes meiosis. And the cycle continues. But this one's a little bit different. And I'll show you why. Oh, crap. Let me fix this. I don't know, let's get rid of, we don't need that. Okay. Okay, so showing you this so far. Okay, what happens once the zygote starts dividing is it divides and it doesn't grow into a sporophyte. No. It stays on the gametophyte and it divides mitotically. So it stays diploid, but it grows into the third stage, life stage. It grows into a carposporophyte. So there's a gametophyte, carposporophyte, and sporophyte. One haploid, two diploid generations. And the carposporophyte is not big, it's little, but it's multicellular. And the only role of this carposporophyte is to produce lots of carpospores. And these are diploid spores. And to do that, when the zygote first divides, half of those cells go on to produce a nutritive base to nurture the carposporangia, which produce the carpospores. So by doing it this way, they develop their own food source and a little habitat for the carpospores to grow up in. Basically, this is a way that this organism can produce a lot more carpospores. So basically, they can produce a lot more individuals from one zygote. It's not just one zygote, one individual. It's one zygote and hundreds or maybe thousands of sporophytes. So it's a pretty efficient way of doing things. And there's a picture of it. There you go. This is from your textbook, or maybe not. But you can see this carposporangia on this nutritive tissue. It's all growing on the haploid gametophyte at this stage. And then the carpospores are released into the environment. And I've already said all this stuff. So basically, carposporophyte is a multicellular diploid generation between fertilization and the sporophyte generation. It increases the number of propules by serving as nutritional support, and it produces carpospores, which grow into the sporophytes. Just a little bit of review there. Okay, so why? Why did they do this? Why did this happen? Well, one of the reasons people think is because this group of organisms don't have motile male gametes. They don't have swimming spermatia. Now, whether or not this is a response to, whether or not this caused it or is a response to it, who knows? But without this third generation, without the trichogyne delivering the spermatia to the egg cell, it would be much more difficult for these organisms to become fertilized. Also, having a multicellular body, zygote body, makes it much more likely that they can produce more spores and produce a lot more sporophytes. I mean, this is kind of a circular argument, right? It's just using the structure to justify why it did it. Who knows? Who knows why it happens? And these things usually happen by chance, and they're just more successful in specific environments, and they stay that way. Okay. So let's have a closer look at that carposporophyte. The mitotically produced nuclei are transferred to this other axillary cell. And this axillary cell goes on to divide and become the nutritive basis. And each fertilized, so from one fertilized zygote, you can get up to 4,500 carpospores. So those are pretty good odds that you're going to have more living individuals. Okay, so we produce these carpospores. They're diploid. They germinate. They grow into the sporophyte generation, and yet here's another term, even though it's just plain old sporophyte generation, they call it a tetrasporophyte generation. This is a diploid generation that undergoes meiosis and produces tetraspores, which go on and germinate and grow into the gametophytes. So it's a sporic meiosis because meiosis happens in the sporophyte, but the only difference is this extra generation, this extra diploid generation just serves to increase the number of sporophytes, the carposporophyte. Okay, so a lot of new terms in this life cycle, but not really that complicated. There's the sporophyte with tetraspores. Okay, so these are the 3 generations: haploid gametophyte, diploid carposporophyte, oops, there's a typo there, sorry, and a diploid tetrasporophyte. Easy peasy, no big deal, right? Okay, well, it is kind of a big deal, and we'll come to that when we start talking about humans and algae. So let's just talk about what these creatures look like, right? I've shown you a couple of pictures, and I've even shown you a picture of coralline algae. These are really weird algae because they have calcium carbonate in their cell walls, so they're really brittle and tough. And as a result, they fossilize really, really well, and they're found as far back as 700 million years. They look a lot like coral, and in fact, they form the basis of a lot of coral reefs because they can grow in really deep water. For example, I think this is from your text. Deepest photosynthetic organism ever found was a coralline alga 268 meters below the surface of the earth. Now that's crazy. I mean, there's hardly any light. There's hardly any light down there. So that organism that they're holding is maybe thousands of years old, right? Because how quickly are you going to grow when it's so dark? But who knows? Maybe they grow. It says they're really efficient at light capture. Maybe they're not that old after all. Makes you wonder that. Another thing about these coralline algae is that there's been evidence of lignin in some of their cell walls. Now, lignin is a carbohydrate, a really tough, very, very long chain carbohydrate that is found in wood, in plants. And it was thought it only occurs in plants. It's only evolved once. And yet here they are in this completely different group, the rhodophytes. They separated from the land plants long, hundreds of million years ago. And here it is again. Very complicated molecule, convergent evolution, very strange. Okay, so one point is a lot of people get confused and they think that red algae is red tide. No. We'll talk about this later. Red algae is not red tide that kills all sorts of creatures. Those are dinoflagellates, which I'm always teasing you with dinoflagellates. I will talk about dinoflagellates. We're just not ready for them yet. Okay, humans and red algae. We actually eat a ton of this stuff. Every time you're eating algae, it's mostly red algae. And we don't just eat it. Well, we do eat agar, right? That's a thickening agent. It's a gel that's used in a lot of cuisines, but it's used also in scientific labs to make plates, as you know. It comes from red alga. Carrageenan, you guys see this on the ingredients list of tons and tons of foods, I'm sure. It's a thickener. It's produced commercially, used very, very widely. It's all over the place. It's thixotropic, an elastic gel that forms spontaneously upon cooling. Like I said, it's found all over the place. It's not bad. I'm not telling you this to scare you or anything. There's nothing wrong. It's totally fine. Nori. People are eating a lot of sushi these days. Nori, this is a great example. I told you red algae it's red, but not always. And especially when this one's living, you can see this person picking it up. You can see it's kind of got a pinkish tint. Even though it's predominantly green, it's still a red alga, even though it looks green. Now, here is a good story. I told you that the carposporophyte was important for humans. Well, nori production crashed after World War II. Obviously, Japan was not in a good state. Up until then, nori was harvested. It was just wild harvested, and that was good enough. But there was a phycologist at Manchester University until she was fired for getting married, Mary Drew Baker. And she studied rhodophytes, and she couldn't understand what was going on. Why couldn't they start commercially producing nori to fill the market? They couldn't cultivate it. They were trying to cultivate it. They're trying to farm it, and they couldn't do it. And it has to do with carposporophyte generation. This is a shell, and you can see this little pink blush on the shell. Well, that was the missing generation. They could not cultivate nori because the the carposporophyte generation in the case of nori, and specifically nori, this isn't true for all rhodophytes, required this habitat of a shell. It had to grow, it had to have the substrate to grow on in order to produce and release carpospores. So they were trying to grow these nori, and they were missing this third generation. They could not get them to grow. Right, so they had the gametophytes releasing zygote, or making zygotes, but the zygote couldn't grow because the zygote needed to grow in a shell. And because of this, well, it's called the conchellus phase in relation to nori production. And after that, nori producers realized they had to include shells in their production systems, right? You can see them down here, and solved it like that. And now, Mary Drew Baker is considered somewhat of a hero in Japan for fixing the nori industry. Okay, so that was really short kind of introduction into rhodophytes. I hope the key points came across, and I'll talk to you later. Okay, who's being really noisy boy over there?